Welcome back. In the previous lecture, we have talked about the basics of quantization. In this lecture, we will start our discussion on quantization with a basic example. The problem is for the following sequence 1.2, minus 0.2, minus 0.5, 0.4, 0.89, 1.3. Quantize it using a uniform quantizer of rounding type and write the quantized sequence. Quantizer range is minus 1.5 to 1.5 with 4 levels. Let's break down the question. First of all, we have a sequence. There are 6 samples. These 6 samples are taken by sampling an analog signal. We have to quantize it. That means we have to find the quantized value of each of these samples. First of all, we have to design the quantizer. The quantizer is uniform. The concept of non-uniform quantizer is not introduced yet. We will introduce it shortly. And also the quantizer is of rounding type. Rounding type means we have to have both quantization levels and decision levels. One thing to note here, the number of decision levels is always 1 greater than the number of quantization levels. So here we have 4 quantization levels. So we have to have 5 decision levels. And also each decision level bisects 2 quantization levels and each quantization level bisects 2 decision levels. The quantizer range is minus 1.5 to 1.5. So the lowest value of quantizer is minus 1.5 and the highest is 1.5. We are assuming mid-rise quantizer here. Mid-rise quantizer, as you all know, have a decision level or decision threshold at 0 value. Here the yellow dots are decision thresholds and the red dots are quantization or representation thresholds or levels. So we have a decision level at 0. First of all, we have to divide this range into parts. Total range is 3 because it is 1.5 in the positive side and 1.5 in the negative side. So total range is 3. We have to divide this whole range of 3 into 4 equal parts because the number of quantization levels was 4. So the number of decision levels will be 5. And we know that 5 levels divide the range in 4 parts. So we have to divide this range 3 by 4, so it is 0.75. We have a decision level at 0, so another one will be 0 plus 0.75, that means on 0.75. Another one will be on 0.75 plus 0.75, or I mean at 1.5. Similarly, minus 0.75 and minus 1.5. These are yellow dots or decision levels. Now we have to place one quantization level between 2 consecutive decision levels. So the first one will be here, the red dot. It is our first representation level. It is exactly in the middle of these 2 decision levels, and minus 0.375 is exactly in between minus 0.75 and 0, and so on. We have total 4 quantization levels. Okay, so our quantizer is ready. Now we have to quantize each sample individually. The first sample is 1.2. We have to choose the decision levels where this sample falls. 1.2 is in between 0.75 and 1.5. So the quantized value will be 1.125. So corresponding quantized value of this sample is 1.125. Here you can see. The next sample is minus 0.2. Minus 0.2 is in between 0 and minus 0.75. So the quantized value will be minus 0.375. So we place a minus 0.375. Then minus 0.5 is also in this range. So another minus 0.375. 0.4 is in this range. So the quantized value will be 0.375. We have a 0.375 here. Then 0.89 and 1.3 both are in this range. So we will quantize them both to 1.125. So this is our quantized sequence. We are done. Then we have already talked about different classifications of quantization. Let's say rounding type, truncation type. We have also talked about mid-rate type, mid-rise type. Another classification of quantization is uniform and non-uniform quantization. In the uniform quantization, all the quantization levels are equally spaced. You can see the spacing between the quantization levels are exactly same, or the quantization step is fixed. But in the case of non-uniform quantization, the difference between quantization levels are not fixed. The quantization step or the gap between consecutive quantization levels are very less in the low value region and as we go to the higher amplitude region, the quantization step increases. So what are the advantages of non-uniform quantization? We will learn about it shortly, but let's talk about something important that we need to analyze this importance first. We have already introduced with the quantization process and quantization error. Quantization error occurs when we are quantizing a sample. Let's say in our example, we are quantizing this value of 1.2 to 1.125, or we are quantizing this value of 0.89 to 1.125. Our quantized sample 1.125 is not exactly equal to 0.89, so there is an error, there is a mismatch between them. This error is called quantization error. So quantization error is basically the difference between the original continuous sample minus the quantized sample, m minus v. So let's analyze what the value of q can be. Let's get back to the example. The step size is delta, so this is delta, this difference is delta, so this difference is also delta. Now let's say our decision threshold are minus 0.75 and 0, and we have a quantization level minus 0.375 in between. So if a sample falls anywhere in this range, we will quantize it to minus 0.375, right? And minus 0.375 is exactly in the middle position of this range. So what can be the error? Let's say one sample is exactly minus 0.375. Then this minus 0.375 sample is in between these two values or in this range. So we will quantize it to minus 0.375, and there is no error because the original sample was also minus 0.375. But let's say the original sample was minus 0.2, as you can see here, minus 0.2. This is somewhere here, minus 0.2. So now when we will quantize it to minus 0.375, an error will be introduced, and this error will be minus 0.2 minus 0.375, and we will get a result here. So what is the maximum error that we can get? The maximum error will be achieved when the original sample is either at 0 or at minus 0.75. Because if it is greater than 0, then this sample will not be quantized to minus 0.375. Okay, the highest sample that can be quantized to minus 0.375 is the 0, and the lowest sample that can be quantized to minus 0.375 is minus 0.7. So what is the maximum error and the minimum error? The minimum error is obviously 0, but the maximum error is delta by 2 on each side, because this is the delta by 2, this difference is delta by 2, this whole difference is delta, so this difference is delta by 2. So the maximum difference in the positive side is delta by 2, and the maximum difference in the negative side is minus delta by 2. So the value of error or quantization error is somewhere in between minus delta by 2 and delta by 2. It cannot be greater than delta by 2. It cannot be less than minus delta by 2. So obviously the quantization error is in somewhere between minus delta by 2 and delta by 2. Also, if we calculate the probability, we will see that the probability of error being from minus delta by 2 to delta by 2 is exactly same. It can be minus delta by 2, it can be delta by 2, it can be delta by 3, it can be delta by 4, it can be 0. Probability of error being all these values between minus delta by 2 and delta by 2 is exactly same. So if we consider a random variable, if we consider this q to be a random variable is a variable that can assume random values in a range. So this value q or quantization error is a random variable, and it can achieve any value between minus delta by 2 and delta by 2. It has a 0 mean and it is uniform. Here you can see, this is the probability distribution. You can see the probability of the error in the range minus delta by 2 and delta by 2 is exactly same always. And the probability of the error being greater than delta by 2 is 0, and the probability of the error being less than minus delta by 2 is also 0. So this is called the uniform RV. These random variables will be further discussed in future courses like digital communication. So if you take that course, you will get better view of these RVs. For the time being, the concept of uniform RV is enough. This is a uniform RV. Here is a demonstration of the original and quantized signal. The blue signal is continuous, of course, and the red one is quantized. You can see it is discretized in the amplitude axis. It cannot have all the values, it has some particular values in this signal. And the error is the difference between this red and blue value, and this is the error signal. Okay, so the error is anywhere in between minus delta by 2 and delta by 2, and the probability of being any value between this range is same. We can calculate the power of an uniform RV, and this is the formula. Don't bother about the formula, just understand that the power of this quantization noise is delta square by 12. Delta square by 12. So if we know the delta, then we will know the quantization noise power. This is the noise power. So remember one thing, noise is unwanted. We do not want noise. So we want to minimize the noise power. We want to minimize the noise power. The noise power is delta square by 12. So if we want to minimize the noise power, we have to minimize the delta. And we can understand it by common sense. Let's say in this signal, let's say this delta is 10. So the error can be anywhere between minus 5 to 5. But if this delta was 6, then the error could be anywhere between minus 3 to 3. If this delta was 2, then the error would be anywhere between minus 1 to 1. So we can see that if we decrease the value of delta, then the error also decreases, and that is what we want. It is true that if we decrease the delta, the error will also decrease. It's true. But if we are decreasing delta, we have to increase the number of quantization levels. You can see the range is always from this value to this value. The range is fixed. So if we want to reduce the delta or quantum size or the step size, we have to increase the number of quantization levels. And the increased number of quantization levels actually means increased complexity, increased time for computation, and all these associated problems. So it is true that if we decrease the quantization step or increase the quantization level, the error will decrease, but it comes with greater complexity. So now we know about quantization power. Now we will derive an important parameter which is called signal to noise ratio. You may have heard this term anywhere in other courses. The signal to noise ratio, SNR, is basically the ratio of signal power and the noise power. Signal power and the noise power. Obviously, we want the SNR to be larger because the SNR is the ratio of signal power to noise power. So naturally, if SNR is increased, that means either the noise power is increased or the noise power is fixed, but the quantization power or quantization noise power is decreased. Either one is good. So we want the SNR to improve. Now let's derive the formula of SNR. SNR is signal power by noise power. Signal power is denoted by P, and the noise power is denoted by sigma q square. We know the value of sigma q square, but it's delta square by 12. We replace the sigma q square here with delta square by 12, and the 12 goes up. So SNR is 12p by delta square. 12p by delta square. So we can see that if we want the SNR to increase, then we have to decrease the delta. So now we have a signal MT that is continuous in the range minus mx to mx. So what is minus mx and mx? Let's go to our first figure. So here is a continuous signal, and you can see the highest amplitude is here, and this is the highest value of the signal, and the lowest value of the signal is here. These two values need not to be same numerically. Let's say this is a sine wave. So sine wave has a same amplitude. Let's say it has amplitude of A, and the highest value is plus A and lowest value is minus A. But for all the signals, this is not true. In some cases, you may have the highest positive value to be 5 and the lowest negative value to be minus 2. This is okay. But for this case, we are assuming a signal that has the symmetry. The positive highest value and the negative highest value have same numerical value. So this is mx and this is minus mx. So the total range is 2mx, 2mx, 2mx. We have to divide it with the number of quantization levels to get the step size delta. So delta is 2m max by L. L is the quantization level. Quantization level is also associated with the encoding process. If we want a 2-bit encoding, then the quantization level will be 2 to the power 2 or 4. If we want 3-bit encoding, the quantization level will be 2 to the power 3 or 8. So, if we want R bit encoding, then our quantization level L will be 2 to the power R. Here R represents the number of bit. So, if we just put this value of delta in our equation here, 12p by delta square. So 12p by delta square, and if you put the delta value here, the delta square will be 4m max square by 2 to the power 2r. There was 12p, and the denominator there are 4m max square. So 12 and 4 we can make a division, and 3 will be on the numerator. So here we have 3. P is here, m max square is here, and we had 2 to the power 2r in here, which will go up and will multiply it with this thing. This will be 2 to the power 2r. This is our SNR value. We can also calculate the SNR in dB. To take dB of any value, we need to take the log of it and multiply it with 10, or in other words, we have to take 10 log 10 in front of it. So if we put a 10 log 10, the second 10 is the base, 10 log SNR here, it will become SNR dB, and in this portion we have two values multiplied with each other. If we put the log here with the property of log xy equal to log x plus log y, so we have log this part and log this part. As usual, we have a 10 in front, so it is multiplied by 10. 10 log 3p by mx square comes from this part, plus 10 log 2 to the power 2r. We know the property of log, that if there is some power inside the log, that power is multiplied in front. So this 2r comes in front, and the rest becomes 10 log 2. If we multiply all this, it will become 6.02r. For simplicity, it is often considered to be 6. We will use this formula in mathematical analysis. SNR dB is 6.02r plus 10 log 3b by mx square. That means this part is constant, because if you take a signal, if you keep the signal unchanged, then m max and p both are unchanged, so you cannot change this part. But if you increase this r, number of bit, your quantization level is increasing. If quantization level is increasing, quantization step or delta is decreasing. If delta is decreasing, your SNR should increase, and you can see that here. If R is increased, SNR is increased. And if we add additional bit to our quantizer, let's say it was 1-bit quantizer and now it is 2-bit quantizer, your SNR will be increased by 6.02. Each additional bit increases the SNR by 6.02 dB. Also, with this increase of SNR, we will need better capacity, because SNR is related to capacity. Higher the SNR, higher the capacity requirement. So we want to increase SNR, but we have to remember that if we increase the SNR, we have to increase the capacity as well. Now, in a special case, if this original signal is a sine or a cos wave, then this p value will be amplitude square by 2. The amplitude is obviously m max, so this p value will be m max square by 2. This m max square and this m max square will be cancelled, and we will have 3 by 2 multiplied by 2 to the power 2r, and in dB it will be 6r plus 10 log 3 by 2. 10 log 3 by 2 is 1.8, so we will have this. We don't need this special case. We will always use this formula, and if we have a sine or a cos wave, we will calculate for ourselves. We do not need the special case.